Hello and welcome back. We'll continue looking at section 4.1 and we'll start out by looking at the law of large numbers. This is quite often misconstrued, so we want to go through this carefully. So as a procedure is repeated again and again and again, the relative frequency of an event tends to approach the actual probability that the event occurs. So as an example, we could imagine that our procedure is, say, flipping a coin. And if we expect that the probability of flipping a heads is 50%, if we flip the coin again and again and again, a lot of times, we would expect to get about half of the coin flips to be heads. Now, this is the law of large numbers, and large means really large. So if you were to flip a coin 10 times, you might expect to get 5 heads, but it wouldn't be unlikely to get maybe 8. That doesn't seem too far outside of the realm of possibilities. If you were to flip a coin 1,000,000 times, by that point you would expect to get about roughly 50-50 as far as the proportion of heads to tails. Now, the law of large numbers does not apply to individual procedures. So again, let's say that we flip a coin 10 times and 10 heads come up. That seems pretty unlikely, but we can imagine a situation where that does. So now we're going to flip the coin one more time, the 11th time. And the question is, oh, well, we already got 10 heads, and the law of large numbers says that things should approach the actual percent. So is it more likely that the next flip come up tails to try to balance out how many heads there are? And the answer is a resounding no. The coin doesn't remember that it was flipped 10 times and came up heads 10 times. If you just walked into the room and watched this one coin flip without knowing this previous information, the coin doesn't recognize the fact that it's been flipped these 10 times. This is called a memoryless procedure, and the law of large numbers doesn't apply to any particular procedure. It doesn't correspond to just one flip of the coin. You can only apply it to a lot of coins, and this is quite often in gambling, where people begin to see patterns in places that they shouldn't and make incorrect assumptions. Another sort of common misconception, not necessarily with the law of large numbers, but just because an event may occur or not, it doesn't mean its probability is going to be 0.5, as in the probability something happens or doesn't happen is going to be 50-50. For instance, if you go skydiving, this may be a bit morbid, but you either die or you don't. It doesn't mean that when you go skydiving, you have a 50-50 chance of dying, because clearly a lot more people go skydiving, and half of them aren't dying. This is clearly not the case. So even though you may be tempted to go, oh, either something happens or it doesn't, therefore it's 50-50, this is an incorrect assumption. The probability that something may happen or that something may not happen is quite often going to be imbalanced. The probability that something happened might be really, really low. So this is just something to keep in mind, that probabilities aren't always equal. So let's do just another calculation, another couple calculations to get some practice. So what's the probability of getting 3 heads in 3 coin flips? So again, what we want to do to find the probability is we want to count how many ways can our event occur versus how many different events may occur. So this probability of getting 3 heads, is simply going to be the number of ways that you can get 3 heads divided by the total number of outcomes. And the reason that I can simply divide these is because each outcome is equally likely. So again, the only reason I can use this formula is because each of the outcomes are equally likely. On any given coin flip, the chance of getting heads and tails is going to be equal. So if I'm going to flip a coin 3 times, any particular pattern of coin flips is going to be equal. The probability is going to be equal to any other particular pattern. So how many ways are there of getting 3 heads? Well, I can just get 3 heads in a row, and that's it. So there's only one way of getting 3 heads in a row. However, how many total outcomes are there? Well, we can enumerate these, just list them down. So we could get 2 heads and then a tail, or we could get the tail in between the 2 heads, or get the tails first. We could get 2 tails and then a head, or if we still get 2 tails, we might get the head in between, or we could get the head first before the 2 tails, or we could get 3 tails. And if you look at the way that I've done this, I've listed them in such a way that, okay, we either get 3 heads, 2 heads, 1 head, or none. So this is it. This is our complete list. And we have 1, 2, 3, 4, 5, 6, 7, 8 different outcomes. So the probability of getting 3 heads is 1 in 8, which will be about 12.5%. Let's look at another scenario here. This will be similar to some of the questions in the homework. So a school is having a vote on some new colors, and students had to vote for a main color, which was either going to be blue or red, and a secondary color, which was either going to be white or gray. So here we have this table describing all the votes. So for instance, 56 students voted for blue and white, 37 voted for red and white, 28 voted for blue and gray, and 13 voted for red and gray. So here's a question. If a student is chosen at random, so each student is equally likely of being chosen, what's the probability the student voted for blue and gray? So again, the probability is going to be the number of ways that we could choose a student that voted for blue and gray, and we're going to divide by the total number of students. So how many ways are there to pick a student who voted for blue and gray? Well, there's 56 different students that did that. So there's 56 different students that I could choose at random. And then the total number of students here is going to be, well, there's 56 students that voted for blue and white. I made a mistake here. This should be 28. If I'm looking for blue and gray, I'm looking for blue and gray, so that's 28. So 28 students voted for blue and gray, but the total number of students, well, there's 56 that voted this way, 28 that voted for blue and gray, like we just saw, 37 and 13, and if we simplify this, this will be 28 divided by 134. So I'm just going to leave this fraction as is. I'm not going to write this as a decimal, although we could do that with a calculator. Here's another question. So the probability that a student chosen at random voted for red. So again, we have to be a little bit careful here. We need the total number of students that voted for red versus just the total number of students. So again here, how many students voted for red? Well, 37 voted for red and white, and another 13 voted for red and gray. So that's going to leave 37 plus 13 total students voted for red. And then likewise, we know that there's 134 students altogether. So this simplifies to 50 divided by 134. So one more thing that we want to look at are complementary events. So the complement of an event which we denote by writing a bar above the A, consists of all the outcomes that are not in A. So the complement you can kind of think as the opposite of an event, but the word opposite may have some other connotations, so we'll try to refer to this as the complement. So the complement of A is when A doesn't happen. So in every situation, either A happens or A doesn't happen. And when A doesn't happen, this is called the complement. So let's look at an example. So flipping a coin 3 times is going to be our procedure. And A is going to be the event where we flip exactly 2 heads. So what is the complement of A? So the complement of A is when exactly 2 heads is not flipped, meaning we could have 0 heads, 1 heads, or 3 heads is flipped. But not 2. So the complement of an event is going to be all the ways in which the event will not occur. So again, here the event is exactly when exactly 2 heads are flipped. The complement of the event is going to be when 2 heads are not flipped, as in it's either 0, 1, or 3 heads. And there's a nice relationship between the probability that an event occurs and the probability that the event does not occur, as in the probability of the complement. The probability of the complement is 1 minus the original probability of the event. So how can we come up with this? Well, we know that no matter what happens, either A happened or it didn't. That doesn't mean that it's a 50-50. It doesn't mean that A has a 50% chance of happening and A has a 50% chance of not happening. That is not the case. What is the case is that something will happen, and it's either going to be A or it's not A. So the probability that A happens plus the probability that A doesn't happen should add up to 1. 1 because something happens, either A or not A. So let's look at an example and we can see this in action. So if A is the event of flipping exactly 2 heads, then the probability of A is going to be equal to, we need to figure this out so that we can figure out the complement of A. And just like before, we can list all of the ways of flipping 3 coins. Either flipping 3 heads, 2 heads, 1 heads, or no heads. And the probability that A happens, we're just going to count how many ways in which we can flip 2 heads, which is 3, and there are 8 different results possible. So the probability of flipping exactly 2 heads is 3 out of 8. So now I want to calculate the probability of the complement of A in 2 different ways. First of all, well, if A doesn't happen, what could have happened? Well, we could have flipped 3 heads, 1 heads, or no heads. And we can see that we have 5 out of the 8 possibilities will correspond to the complement of A. But we have our handy formula. The probability of the complement is 1 minus the original probability. So let's do this in a different way. This is going to be 1 minus the probability of A. And we know that this is going to be 1 minus the probability of A, that's 3/8. And 1 is the same thing as 8/8. So 8/8 minus 3/8 is 5/8. And we see that we get the same answer. So the probability that an event doesn't occur is simply 1 minus the probability that the event does occur.